Okay, just a quick revision of last lesson. We spoke about heat and temperature. We spoke about the difference between heat and temperature. We said that heat is the overall energy given to a substance. And we said temperature is the local energy or the local vibrations. How much heat energy is in that section of a substance. That's the temperature. We defined the three scales. We said the Fahrenheit scale, we used the Celsius scale, and we talked about the Kelvin scale. And then we finished off with the three methods of heat transfer. We said conduction, convection, and radiation. Conduction was the passing on of heat energy by vibrations. So this atom vibrates, then that, then etc. So conduction usually occurs in solids. And then we have convection, which occurs in liquids and gases, where the atoms are actually free to move. So they pass on the heat energy by flowing around. And when they heat up, it becomes less dense, so it rises. And when it gets colder, it sinks. So you get these things called convection currents. And then we spoke about radiation, like the heat from the sun. There's actually nothing between the sun and the earth, and the heat packets travel. There's no atoms in between, so you don't need atoms to pass on radiation. And it takes the heat packets around 8.5 minutes to reach the earth from the sun at the speed of light. Today we're going to talk about the two types of waves. The two types of waves are longitudinal and transverse. The first one I want to say is transverse. And transverse is the one where, imagine if you connect a rope to a tree. And you're here and you're trying to swing the rope. And you're swinging the rope like this. So what's going to happen is the rope's going to have this transverse wave in it. Transverse just means the energy is going to travel perpendicular to the movement of the particles in the rope are going to travel either up or down, right? So if you're in the rope, you're either going to travel up or down, but the energy is flowing from my arm out. So the energy is flowing this way, like this, but the particles in the rope is only going to move up or down. So I'm passing the energy onwards, out, but notice how this part just moves up or down. So transverse means when the particles are moving perpendicular to the energy, to the flow of energy. So the particles in the rope move either up or down, and the energy moves 90 degrees to it, like a right angle. That's the definition of a transverse wave. Today, though, we don't want to talk about transverse waves. That's later on, Year 11, Year 12 physics. Today we want to talk about the easier one, which is longitudinal waves. Longitudinal means there's a compression and a rarefaction. So there are two components. We'll draw the diagram soon. It just means the energy flows in this direction and the particles actually vibrate in the same direction as the energy flowing. So, for example, sound, and that's where we're coming to. When you speak, my vocal cord vibrates, and they vibrate the air molecules. And the air particles move like this, they vibrate like this. And that one vibrates the next one. And then that one vibrates the next one. So eventually, those vibrations travel in the air, and it comes to the person's ear. And it enters the ear, and your eardrum actually vibrates like this. And then the three bones inside your ear, the three smallest bones in the human body, they kind of knock onto the hearing organ. You don't need to know about that for now. Basically, longitudinal means the direction of the particles is parallel to the direction of energy. So if there's an energy flow in this direction, then the particles are actually moving like this to pass it on, like dominoes. There's a flow of energy, and the only direction that dominoes move is that way, not up or down. Up or down would be transverse, side to side, push and pull, basically, push and pull is your longitudinal wave. And a good way to do this is, if you have a slinky, you do this with a slinky. You push and pull, so you'll actually see a wave that travels to the other side. Even though all you're doing is this, you'll see the wave that travels through and it'll bounce back. And we're going to talk about that bounce back action too. So sound is a very good example of a longitudinal wave. Because when we speak, we vibrate the atoms and they move in the direction of the flow of energy. In fact, sound travels outwards like this from us. So everyone in the room can hear us. The closer you are, the more energy your sound wave is going to hit your eardrum. The further you are, obviously, the more energy you need to reach them. So that's what sound is. If we are to draw a little diagram of sound, imagine these to be your air particles. So there's going to be a region of a lot of air particles, and then that's your compression. All those air particles are compressed. And then you have this region of comfort. That region is called rarefaction. And guess what comes after that? Same thing. You have your high density area again, which is just called your compression. Because if you're trying to send energy like this, as soon as you do this, all these air particles are compressed. And as soon as you pull back, they're now stretched out. And that's how sound travels. You have these traveling compressions and rarefactions. And then these compressions then is like the high pressure section of the ear, and the rarefactions are the low pressure section. Before it gets too confusing, I'll move on to echo. And you don't need to know too much about sound waves. Basically, if you had a speaker, when you look at a car, for example, and they have a subwoofer in the back, and they put up the bass, you see the sub go, you actually see the speaker, the cone, moving up and down. And you'll only see it if it's a very low frequency. I'm going to talk about that too. But basically, if it's a very low frequency, you'll actually see it with your own eyes, how it's moving up and down. And every time it moves up, it squeezes the air, and that passes on the energy upwards. And then every time it moves down, it stretches the air. So it's creating compressions and rarefactions, which vibrate your eardrum in turn. So what happens when those sound waves hit a surface? They're going to come back. They're going to reflect off a surface. If it's solid, it'll reflect. We call that echo. So in a small room like this, you won't have any echo because the walls are actually very close. But if you go to the mountains, for example, and you say, hello, after a second or 2 seconds, you hear it go, hello. You'll hear your own voice back again. Because there's just a straight path of sound to travel, and there's no reflection, there's no mirror basically for your sound wave until it hits the mountain. And because sound travels at 330 meters per second at room temperature, if those mountains are a kilometer away, it's going to take your sound 3 seconds to hit the mountain, and then 3 seconds to come back to your ear. So it'll take you 6 seconds. So you'll say, hello! And you'll have to wait 6 seconds for your sound to, hello! Come back to your ear. It'll obviously be less stronger than how you said it. It'll be a bit weaker. So that's the speed of sound in around room temperature. Because sound reflects off surfaces, we can actually use this in technologies such as sonar, which is sound, navigation and range. It's short for sound, navigation and range. What sonar does is, for example, if you have a ship and you want to see if you're about to hit, I don't know, if it's shallow. Say you're in a ship and you want to maneuver around shallow areas so your ship doesn't get stuck. So you have a sonar beam under your ship, and you're constantly checking how deep the surface, or how deep it is, or how shallow it is, by sending out a sound wave and seeing how long it takes to come back. Because you know the speed of sound, you know the speed of sound, then you can calculate the distance. So that's sonar. We can use that technology to see how deep, or even in fact, if there's a school of fish, or if there's a submarine coming, you see it in movies, it goes beep, beep. Basically what you're doing is you're shooting out a sound wave, and it reflects off something. And you continue that, and the next time you shoot a sound wave, it's a bit closer. So it quickly calculates the distance because it knows the speed of sound. So you can actually use that to see how far away objects are.